here, like typical question. For example, for the pop quiz, this question is on the pop quiz. So it's going through the details of a mass spectrometer. So if you have a mass spectrometer, if you look at my big idea, so have that slide ready next to you when you're going to do the test number 3, because I try to summarize everything. In addition to that, when you look at your equation sheet, okay, some equations are missing. So you want to collect all the missing equations and have them in your equation sheet. So it's going to be ready for you when you're going to do the assignment or the test number 3, right? Or even the final. Because some equations are not there. So make sure you have all the equations. For example, I'm not sure if this equation is in your equation sheet. So that will be for a mass spectrometer. So when you have particles and they have to be charged entering a magnetic field, and the magnetic field is perpendicular to the velocity, the magnetic field will exert a magnetic force that will deflect the particle. So typical conceptual question. A magnetic field deflect. An electric field accelerate or decelerate. Okay? So according to their mass, so if a particle has a large mass, it's going to be curved here, but not as much as a small mass. So you see the radius here depends on the momentum. More momentum, harder it is to deflect because it has more momentum. So it's like a truck going really fast on the highway, hard to make a turn. If it has a small momentum, small mass, or small speed, it's going to be easier to deflect. And then the radius is inversely proportional to the charge and the magnetic field, because these are the motivation. Okay, so you can tune the magnetic field, you can change the magnetic field. As you increase the magnetic field, you make it curve more. Okay, but you want to make sure that all those isotopes, okay, will have the same velocity when they go inside the magnetic field. So the only difference will be the mass. That way you can find the mass of an isotope, or you can sort out isotopes according to their mass. So all of them need to have the same charge and the same mass. For that, we use what is called a velocity selector. Okay, so before that, you need to accelerate the particle, the charged particle, using electric field, right? So the potential energy will turn into kinetic energy. So you speed them up with an electric field, and then here they're going to go through a velocity selector. So all of them will have the same velocity, and then it goes inside the magnetic field. Okay, so we did that last time. I just want to review. So there will be a question on test number 3. So what's a velocity selector? So you can, let's do just the conceptual part here. Okay, so the type of questions you might have for the MCAT, right? It's totally conceptual. So let's say this is positive. Let's say it's a positive charge. And you have both an electric field here going up and a magnetic field going towards you. Are you with me? So it means towards you, out of the board, right? So if it's a positive charge, F equals QE, you see the force will be, because of the electric field, it will be up. Do you agree? That will be QE, right? Because an electric force is always along the electric field if the charge is positive. Against the electric field is the charge is negative. Let's look at the magnetic force. So you take your right hand again, right? So the velocity is going this way. The magnetic field is going towards you. So the force is velocity this way, magnetic field towards you. So the force is down. Okay, so velocity, magnetic field, force. The magnetic field, the velocity is going this way, the magnetic field is going towards you, so the force is down. The force is always out of your pole. Okay? Velocity, magnetic field, force. The right hand rule. That is what's current. Yeah, but the current is a moving positive charge. So we have seen you use the same pole whether it's current or moving positive charge because the current is made of positive charge that's moving. So the QVB. Yeah, so that could be velocity or current. Velocity of a positive charge. If it's a negative charge, you use your left hand. Agree? You can use your 3 fingers as well. It works. So velocity this way, or current this way. Magnetic field towards you, the force is down. If it's a negative charge, you can use your left hand. Okay, so the magnetic force will be down. And it's going to be QVB. So I'm going to put just the magnitude here. And then you're going to tune the magnetic field in such a way that they're going to balance out each other. So now it's going to go along a straight line. So you're going to have QE equals QVB. Okay, so that way you can select the velocity that you want, and you want to make sure that all the isotopes entering the magnetic field region have the same velocity. Okay, before using a mass spectrometer. Do you agree? You can easily change the magnetic field because you can use an electromagnet. Okay, so if you increase the current, the magnetic field will increase. So it's easily done by tuning the magnetic field. So this is called a velocity selector. Are you with me? Okay, so question on test number 3 about that. So you accelerate the isotopes using voltage, right? And then they go through a velocity selector, so all of them have the same velocity. The only thing they do not have the same is going to be the mass. Then it goes through that magnetic field. It's going to be deflected, and you can sort them out. You can move a detector, and if you hear the click, then you know the radius. If you know the radius, then you know the mass. You have this equation. Is that clear? If you are interested, I highly recommend that you watch that video. I think it's from Physics Ninja. It's like a nice YouTube channel. Okay, any question? We're good? Okay, so this is called cyclotron motion. So any charged particle inside the magnetic field, only and only if it's moving, only and only if it's moving at a right angle relative to the magnetic field. So you need to have a component of the velocity perpendicular to the magnetic field. Otherwise, there is no force. Remember, if you have a magnetic field this way and the velocity that way, there is no force. If you have velocity this way, magnetic field opposite direction, there is no force. It has to be at an angle. Okay? So then you have a force here. It's like a centripetal force, right? It cannot change the speed of the charged particle. It can only change the direction. Okay, so it's like a centripetal force. Okay, that's how we get that equation. And we can also find how long does it take to make that cycle here, to go around. So that will be called the period. The period is the time for one cycle, and you have the equation here. Okay, so the velocity, remember from physics 1, velocity, okay, is the distance over the time. In that case, it's going around. So the distance around the circle is 2 pi r, and the time is always the same. It's going to be the period. So the period, the unit is in seconds. You can define also the frequency in hertz, and the frequency is 1 over the period. So this is the time for one cycle. This is a number of cycles per second. Agree? Okay, so again, you have to skim through the slides and collect all the equations that you see that are not in the equation sheet. So you can complete the equation sheet. Okay? So you have the period. So interestingly, here you see that equation here, everyone can see it. So the time to go around does not depend on what is missing. We have B, okay? We have the charge, we have the mass, but there is no velocity. Very good. The period does not depend on the velocity. Okay? So that takes us to what we call a cyclotron. So first of all, I forgot to show you a nice demo here.
We're sitting here in the car. We're going to show you.
So here you have two coils. Between the two coils, you're going to have a magnetic field. So remember when we had a capacitor, you have two plates parallel to each other, and you had a uniform electric field in between the plates. Likewise, here you're going to have a magnetic field, which is uniform. So uniform magnetic field, the magnetic field goes into the screen or out of the screen. If you go back to big idea, I think I have a slide somewhere. Okay, that's called a static magnetic field. So you have two coils like electromagnet parallel to each other, and in between you can generate a uniform magnetic field between the two coils. Okay, it's called Helmholtz coils. Okay, so that's what it has here, and he's gonna send. So here you have a vacuum tube, so he's gonna connect that to a power supply with a cathode, and you're gonna have an electron beam.
Charge particle, turn people in a circle. You put it in the uniform magnetic. This is an evacuated glass bulb. There's a light pop going. I'm going to play this game. If you didn't know.
Wait, that's no, sorry.
Hold on.
Let's go back.
Here at the car, I'm going to show you. Charge particle beam doesn't need to go in a circle. You put it in the uniform magnetic field. So this is an evacuated glass bulb. There's an electron gun. Electron gun really just means a heated metal filament. It's easy to draw electrons off of. Near the gun that you can now see glowing orange is a little metal plate with a large positive potential that sucks the electrons up to a few volts at the plate. The plate has a hole that some of the electrons keep going.
So you have your beam of electrons. This is the cathode, and on the other side you have the anode.
Light from the gas. There. Now we know that we plug it nearby, and we're plugging. Here's my north-south arc magnet. If one pole pushes it up, pull down, I bring it in, these kinds of things. That's what these two big coil.
So you see the beam of electron is this direction, and you have the magnetic field in the screen or out of the screen. So the force has to be perpendicular to both. Okay, it has to be perpendicular to the magnetic field, perpendicular to the velocity.
Current is coil. See what pattern the electron beam is. Here, we'll bring it up.
You see, it's increasing the magnetic field. And as you increase the magnetic field, you increase the motivation. So the curve is getting smaller. So you see, it's going into a circle around the magnetic field lines. Magnetic field lines are going into the board or out of the board. I don't know, maybe this screen is better, but you see this is the beam of electron, and you can define how long does it take to go around. That will be your period, and the radius r is here.
Back, zero, back down zero. So
So that takes us, okay, see, I have a screenshot, the same thing here. Large Hadron Collider, I show you the video. So, and we already talked about the cyclotron. So it's a big deal because it's used in hospitals to make radioisotope. So that means radioactive nuclei that have a very short life. So they use that for PET scan, or they use that as a way to trace a tumor inside the human body, right? So they need those radioisotopes. And how do they make those radioisotopes? They have to use, they have to make them in the hospital, right? So they're gonna shoot, for example. So they need something to shoot, like it's like a gun. Think of it like a gun, right? That's gonna send a projectile, which is a proton in that case, at a very high speed. So very high energy. Okay, you send it to hit, for example, here a nitrogen molecule which is not radioactive. Okay, so it's a nuclear reaction. Out of that reaction, you're going to have carbon 11, which is radioactive, but a very short life. And then you give that to a patient, mix it with sugar, for example, and it will go to the tumor, God forbid. Inside the tumor, it will burst gamma ray from inside out, and you can have a PET scan, or you can just follow the beep 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 beep, right? You can, it's called a radio tracer. You can trace the location of a tumor thanks to that. So you need to make those radioisotope, radioactive nuclei, and they have a very short life. So if we are talking about PET scan, those radioisotopes, they decay very quickly inside the body, and they will decay, giving a positron, an anti-electron that combine with electron inside the body, and you will be highlighted by gamma rays from inside out. So anyway, my points, you can look it up. Radiopharmaceuticals, big deal, big hospital, they all have those cyclotrons. So you use those cyclotrons to accelerate charged particles to a very high speed. Okay, so as it's going around, you see, you're going to push it with an electric field, go around with a magnetic field. Push it with an electric field, go around with a magnetic field. Push it with an electric field, go around with a magnetic field. So it's going to go faster, right? You can use that for proton therapy. Okay, when they are doing proton therapy, for example, you need very fast moving proton. Those proton is better than X-ray because when they go to the tumor, they don't destroy healthy cells on the way. They just deposit their energy just inside the tumor and not on its way. Except it's more expensive, so insurance will not pay for it unless like in a desperate case, or I don't know how you can get insurance to pay for it. But otherwise, they say, oh, okay, do the X-ray therapy first. But proton therapy is a very nice way to kill tumor because you take the proton, you accelerate it, make it go faster, boom, and inside the person. Okay, so this is called a cyclotron. I don't know, have a simulation. No, it doesn't look like it's I had I had a simulation, but I don't know where it goes. Here, maybe here, yes. So you have your proton for a proton therapy, for example. You start from here. It's going to be accelerated by an electric field, curved by a magnetic field, and then it's going to go really, really fast. The electric field is between this gap. And then the magnetic field is, you see, you have south here, north here. So you have a magnetic field going from north into the south. So the magnetic field will deflect the electric field here across this gap will push. So you push, deflect, push, deflect, push, deflect. So it's like a swing that you are pushing and pushing and pushing. So it's go faster and faster and faster. So use that as a gun. Okay. So you're going to use different radioisotopes depending on which area of the body they want to look at, they want to see. So for example, oxygen is for the brain. They use oxygen. So they have to make radioactive oxygen. Fluorine is for the thyroid. Fluorine. Do you say fluorine or fluorine? Fluorine, that's how you say it? Right? Fluorine is for the thyroid. Okay, if you want to have a PET scan here. Okay, so it's a particle accelerator, except it's not linear. It's used in research and for PET scan. Okay, so now the motion of a charged particle inside the magnetic field. So each time you have a magnetic field and you have a particle here moving, and it has a component perpendicular to the magnetic field, then the particle wants to go around the magnetic field. It wants to circle around the magnetic field lines. Okay, so this is called a helical motion. I don't know if I have a picture. Something like this. So you send a particle inside the magnetic field. Okay, so it has some velocity in this direction, some velocity perpendicular to the magnetic field, so it's going to circle around. As it's going to circle around, because it's an acceleration, it's not going faster, okay, but it has an acceleration because it's changing direction, so it's called centripetal acceleration. Each time you have a charged particle that is accelerating, it's going to radiate. Okay, so you're going to have some radiation. And this radiation, for example, for the Earth, this is called the Van Allen belt. So those charged particles coming from space could be electrons, could be protons, very bad for us. Thank God we have the magnetic field to protect us. So those charged particles, they're going to be trapped here. So they're going to circle around the magnetic field lines. They're going to accelerate, slow down, and then reverse their motion. When they are doing it, they're going to burp out their energy that they are losing. That energy is going to be into photons, right? Colors. So these are called the Van Allen belt. And it was seen for the first time in 1958 when they went to space, because there was a space race between Soviet Union and the US. So that was, I think, the American who saw them for the first time. Is that clear? Isn't that cool? Okay. See protons coming from space and they cannot reach the Earth. Okay, it's going to be trapped. It's going around the magnetic field lines. Why it's doing so? It's going to emit light, okay, because it's going to emit radiation. It's going to lose energy, okay? So it's like a shield, okay? The magnetic field of the Earth is like a shield. Okay, we're almost done with this unit here. Okay, lots of applications. You can use a magnetic field to trap plasma. Okay, so those charged particles could be hydrogen nuclei, gonna be trapped inside that magnetic bottle. It's like a container, and you do that with magnetic fields. Okay, to keep deflecting the hydrogen nuclei that keep moving around a circle. It's called a tokamak. Okay, the magnetic field line again. So here you have a microwave. So microwave is a very smart technology, and it's using what is called a magnetron. So magnetron. So the magnetron is what is inside the radar. So what's a radar? It's sending a microwave, okay, and the microwave will ping an airplane, and it will bounce back, and you know the location of the airplane. So this radar was developed during World War II by the British, and it was highly classified. Only the British had the technology. So when Nazi Germany was trying to invade England, all of a sudden you had thousands of pilots, right? And they didn't understand how come the British were so fast to react. And they thought maybe there are many of them and we underestimate how many pilots are available. It's because they had the radar, and Germany didn't have the radar, so they could ping the airplanes when they were trying to invade England. At the end of the war, it was disclassified, and they gave the technology to the American, who it took them a while to understand how it works, right? And once they understood how it works, they use the same technology that they use in a radar in a microwave, because you have to make money somehow. That's the goal. And it was in the 1950, microwave made big entry in all the kitchen, right? But it's using a magnetron. So how does it work? Okay, you have an electric field and a magnetic field. So you have a beam of electrons. It's not really a beam, it's just electrons breaking free from a very hot filament. So that will be the cathode. Here you connect to a power supply between here and there, right? So power supply is 5,000 volts. So the electric field will accelerate the electrons, and at the same time, you're going to have a very strong magnet that will deflect the electron. Okay, so the electrons are deflected and they start to oscillate back and forth in a circle, back and forth, because it's AC. And because they accelerate, not that they accelerate, but they go into a circle, they're going to radiate microwave. Okay, so it's just a way to transfer energy from the power supply, 5,000 volts, to the microwave. And the microwave has a given energy of, and I forgot what's the microwave energy, I forgot, but it has a given frequency. So let's ask. I think gigahertz. 2.45 gigahertz. So you go from a power supply 5,000 volts, so 5,000 joule per coulomb. Okay, you transfer that to the energy inside that microwave. The microwave, it's a wave, right? And that energy is inside that microwave, and that you use that to heat up the food. So there is a transfer of energy from your power supply to the microwave to the food. So if you are interested, I think in Canvas you will find a video that explains how it works. But super smart technology is not, once you understand the physics, you understand how it works, but it's super smart because it took a while for American to understand how they did it. It's the British. Okay, so lots of application as well. You can use, for example, I think it's also in the, maybe in the pop quiz, not pop quiz, test number 3. You see, if you have current flowing here, right, and this is a conductor, and you see the magnetic field from the bar magnet, so out of the north into the south. Magnetic field goes into the south, out of the north. So you can use your right hand to show that positive charges will be pushed in this direction, negative charges will be pushed in that direction. Okay, you can use your right hand. Okay, let's try to do that. Use your right hand. The current is going this way. Magnetic field is going that way. Yes. So the positive charge is going to move this side here, on that side. Yes.
How, how do you like say the car is going like clockwise or anti-clockwise? How do you like what way do they go?
No, so the magnetic field, the rule is magnetic field always go out of the north into the south. So it's not clockwise or anti-clockwise. It's just out of the north into the south. Always.
Don't you always point like for the north basically?
No, it depends. It depends on the magnet. So the current is going this way because it's a given. So it depends how is your magnet. If you place the magnet like this, it's going to be a different configuration. Out of the north, into the south. Out of the north, into the south. So magnetic field is always circling around. Out of the north, into the south. So in that case, out of the north, into the south. So the magnetic field is going this way, the current is going that way, so the force will be there. Yes. So the magnetic field is going this way, magnetic field is going this way, the current is going that way, so the force will go that way. Current going this way, magnetic field going this way, the force going that way. It has to be in 3D. The force is perpendicular to the current, perpendicular to B. The force always perpendicular to B, and the force is always perpendicular to the current or to the velocity. Right? Current, velocity, current is just positive charges moving. Okay? If the velocity is parallel to B, there is no force. Okay? Yes.
Sorry, I was just wondering if you could do or once again the hand. Okay, it's so confusing for me.
Okay.
I'm so sorry.
If if you use your right hand, if this is the moving charge
Mm-hmm.
or the current,
Mm-hmm.
it's a vector, so it has a direction.
Mm-hmm.
If this is the magnetic field going this way,
Mm-hmm.
this way, the force comes out of your pole like a tree,
Okay.
like a drawing tree.
Mm-hmm.
Okay?
So current, magnetic field, and then it's going towards it.
Yes.
But the magnetic field is that way.
Yes.
Okay.
So it doesn't have to be the current, it could be a moving positive charge.
Okay.
Magnetic field
Mm-hmm.
can do this. The force will be like a tree growing in your palm.
Okay.
Out. So in that case, the current is going this way, and magnetic field is going up.
So the force is
This way.
okay.
Right?
Okay, perfect.
You can use your 3 fingers. The current, magnetic field, force.
Okay.
Right?
Mm-hmm.
So imagine you have a tree growing out of your palm. It's growing. Did you all get that? So be careful with the magnetic field. Magnetic field is not the same inside, but it's always out of the north into the south. So if I ask you for the test number 3, if you have a coil, right, if you have loops of current, you take your hand here, goes around, that's the loop of current. Here it's showing you the north. That's the north and that's the south. Out of the north into the south. Out of the north into the south. Okay? And you can use the slides. Big idea here. If you go back, I have all the right hand rules here. Okay, if this is the current or this is the moving charge, the magnetic field will circle around. That's your magnetic force coming out of your palm. And that's if you have a coil, it will behave like a bar magnet, north and south. Okay? You survived? Okay, if you survive, it's good. Okay, so the force, the magnetic force is always perpendicular to the magnetic field, perpendicular to the current. If the magnetic field is parallel to the velocity or to the current or anti-parallel, no force. So the magnetic field, the magnetic force, sorry, is a high maintenance force. You know, high maintenance, high maintenance. So my gecko, for example, is a very low maintenance pet, but my daughter has a border collie. This is a very high maintenance dog. So magnetic force is a high maintenance force. It needs to have a charged particle. The charged particle has to be moving, and it has to be moving in a direction one with an angle with the magnetic field. It needs to make an angle with the magnetic field. Otherwise, no force. So electric force is a low maintenance force. Okay, anyway, lots of applications. So here you can compare electric field and magnetic field. Again, the magnetic field deflect. The electric field accelerate. You cannot have a north by itself. You cannot have a south by itself. It's always a north with a south. So this is called a magnetic dipole. A loop of current here will behave like a magnet with a north and a south. That's a magnetic dipole. You can have a positive charge by itself. You can have a negative charge by itself. You can have in the water molecule a plus and a minus, and that will give you an electric dipole. Very important in chemistry. Okay, we good? So, magnetism, the source for magnetism is really moving charges, right? The only thing that can create magnetism is because some charges are moving. So inside a permanent magnet, okay, why do we have a magnetic field? It's because of the electrons spinning. It's the spin of the electrons that will create the magnetic field from a permanent magnet. So the source for magnetism is moving charges. So that comes from your book. Okay, so if I go back to your book here, you see magnetic force and magnetic field, that will be the unit 21. So I highly recommend that you not only rely on me, like some students, they just rely on me. Don't rely on me. Yeah, you have a textbook, and you can see that many of those pictures that I use in my slides come from that book here, right? So I recommend that you go over it. Okay, you can read. It's a very nice reading. So you see north, geographic north is the magnetic south, out of the north into the south, out of the north into the south. Okay, that's I have that in my slide, and so forth. See, and so on. Okay, so we did all that. See, we did that. See, you have the current, the magnetic field, that will be the force. Okay, so at the end, you have a summary of everything here, and you can review. That will be the magnetic force. Okay, that will be the radius, motion of a charged particle in the magnetic field, and then the mass spectrometer, that will be the equation, the force on the current carrying wire, and that will be the torque. You see, you have all those equations. So again, I'm going to repeat myself, but you should go back and collect all the equations that you don't see in your equation sheet, and you can add them up. So you will save some time when you're going to do the assignments. Copy me? Are we good? Okay, so we're going to talk about, so we are unit 3.2. So it's going to be easy because it's a review. Except that now I'm going to have some equation included. So source of magnetism. So this right-hand rule, we already seen that. If the current is moving this way, the magnetic field is going to curl around. Very close to the wire, the magnetic field will be very strong. As you move away, it's going to decrease. Okay, the relationship is inverse. It's an inverse relationship. So as you multiply the distance by 2, the magnetic field will be divided by 2. Okay, so if you make a drawing here, you see close to the wire, the magnetic field lines will be packed together just to show that it's going to be very strong. And as you move away, those magnetic field lines are spreading out. Understand that the magnetic field cannot diverge, cannot converge, it's only curving around, circling around. It's curling. Okay, so that will be the first equation. Again, I told you, start collecting equations. Here is the equation for the magnetic field produced by a straight wire. It has to be straight. If it's not straight, then you have to go to calculus. But if it's a straight wire, it's pretty straightforward, and that will be the equation for that. I'm introducing here a new constant, mu0, which is 4 pi times 10 to the negative 7. So that will be the equation for the magnetic field, okay, produced by a straight wire, current carrying wire. It's inversely proportional to the distance, proportional to the current. And if I substitute here mu0 by this value, I get that equation here. So maybe this one is easier for you. Okay, so on your equation sheet, okay, you add your little hand, B equals 2 times 10 to negative 7 times the current divided by the distance R. Okay, this and that is the same thing. This one is easier. Are you with me? It's a simple equation. So you can go here. I have the summary here. So if you have a straight wire, it's going to produce a magnetic field around. That will be the equation for the magnetic field, or that will be a shortcut here. Except I'm missing the current here. You should have I there. I'm missing the current I. So anyway, let's take an example. Okay. Let's do number 1. Okay, let's do practice, because if you stare and you're gonna space out, you're gonna fall asleep. Let's do that. Okay, So what's the equation? B, the magnetic field produced by a straight wire. So you have a current I. Okay, so this is a wire, and you connect that wire to a power supply somewhere. So you see that's going to be your plus, that's going to be your minus, and you're going to have a magnetic field here going this way. You take your right hand, it's going to circle this way. Okay, we already did that. It should go this way. And the equation is, so B of a wire, it's going to be, so either you write it this way, 2 pi r, or you write it this way, 2 times 10 to the negative 7, the current I over R. Okay, so this is in meters, this is amps, and this is the magnetic field, Tesla. Okay, so you can do it. So a magnetometers to measure the magnetic field, place 1 centimeter away from the wire, so R equals 0.01 meters. You have B, okay, which is 0.3 times 10 to the negative 3 Tesla. How much current? So I question mark. Okay, so just plug it in. Make sure that you have this equation in your equation sheet. Okay, so can you plug it in, doing it? And you should review, because if you keep forgetting over the weekends, we have only a few weeks left. So bear with me, we are almost done. Don't forget everything. Yes.
Say 0.3 or 0.8.
0.3. Okay, so 0.3 times 10 to the negative 3 equals 2 times 10 to the negative 7 times the current divided by 0.01. And then we will check the equation sheet to see if this equation is there or not. Okay, so are you doing it? 4, 5. What did you get? 15. Yes, very good. 15 amps. Okay. Now, if you look at your equation sheets, we can check if it's there or not. Let's see. Da, 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 da. Oh, it's is it this one? Yes, it's this one. Okay, this one. Except it doesn't say it's from a wire, but it's that one. So you should put here wire, okay, because we're gonna have a coil. So this is from a wire. Okay, just for you to visualize, to make sure you understand what's going on. So you have to imagine those circles here, they are all the way around. See that the magnetic lines are packed together when it's close to the wire, and then it's spread out because the magnetic field gets weaker. So for test number 3, you will have something like this. Again, you take your right hand, the current is going into the ball, so it's going to circle this way, clockwise. Okay, you can show that. We already did that, but I guess it's lots of conceptual questions. You see, you can see it's going this way. A compass is like a vector. Okay, this is the head, that's the tail, and showing you how the magnetic field is going around. Yes.
It says the super green. So then, technically, in this case, my thumb, I guess, would be going towards the negative.
No, you're using this. So this is the wire, and that's going to be the magnetic field.
Okay, but then.
So the thumb is the wire going into the screen.
Okay, but like, I know it's going. And hopefully this is not another question. I know it's going that way because the negative is towards the end.
Yep. No, you know, because current goes from plus to minus.
Okay, thank you.
Okay, so the plus is here, the minus is there, so the current is into the board. So this is I, and this is B going around. So the equation says find B, for example, at a location R. Okay, so at a location R, it's going to be the same B all around. It's going to be the same B.
Okay.
So when you are using the equation, you are just finding B, okay, equals, what is it? 2 times 10 to the negative 7 times the current over R. So you are just finding the magnetic field here at a distance R from the wire. As you increase the distance, B is going to decrease. Okay? Okay, so where are we now? I don't know if we're going to do a... Okay, let's do the number 2. It's easy now. It's just you plugging in, right? So let's see, the current is going this way. So the magnetic field is circling around, right? So first it's going to be very strong, and then it's going to decrease. So the magnetic field is, if I use my shortcut, 2 times 10 to the negative 7, the current over the distance. So that's a distance from the wire. So that's a distance R. Agree, everyone? It's like an aura. A magnetic field is like an aura produced by the current. So at a distance R, that's going to be B. So B, okay, it's going to be, so the direction will go this way. If this is north, because it says north, north. So B equals 2 times 10 to the negative 7, 6, and that's going to be 0.12.
I got 1.35 times 10 to the negative 5.
So 1.35?
Times 10 to the negative 5.
Okay, did you all get that? Yes? Okay. Okay, so that's easy. Okay, that's easy, right? You just plug it in. So the only thing is that I see there is a typo here. So you can use that equation here. This is the shortcut, but you need to put I here. I forgot to put the current here. Okay, you need to add I. Agree? Otherwise, you can use that equation with mu 0 4 pi times 10 to the negative 7. Okay? Are you with me? So make sure you add in your equation sheet, right? You add this. B of a wire produced by a wire is 2 times 10 to the negative 7 times the current over the distance from the wire. Okay?
Is it okay to ask when would we use the 4 5 one?
But you can use it. It's just I'm giving you, yeah, you can use it. You can use that equation instead. Because this is 4 pi, so it's simplified into this, but you can use that instead.
Oh, I see,
Right? Because mu 0 is 4 pi times 10 to negative 7, so it's just simplified into that. Okay. So let's try to do this. Can you do it? Don't stare. Why is it that you are staring? Don't stare. Please do. I understand. This is so bad to have physics 2 p.m. after lunch. At the end of the day, you are digesting. It should be taught like in the morning, and then you have biology in the afternoon. That will be better. Okay, so it's a 2 steps problems. First, you find the magnetic field produced by a current, and then you find the magnetic force. Okay, so you have a positive charge here placed there. Okay, you have the magnetic field from the wire, and the charge is moving this way. So let's make sure we understand. So you have the wire, magnetic field going around. So that's going to be the magnetic field. You have a positive charge moving this way, positive charge this way, magnetic field that way. The force is going to be to the left. It's a centripetal force. So the first step, find the magnetic field produced by the wire. The first step. Don't stare. Do it. Otherwise, I'm gonna get mad. Do it. Help each other. Talk to each other. You don't need to sit at the same place. You can move around. Don't have inertia. Be rebellious. Change spot. So the magnetic field is from the wire 2 times 10 to negative 7, the current, and the distance. I'm going to put wire here. So first we're going to find that magnetic field here produced by a straight wire.
Is it 1.2 to the negative 5?
Yeah. 1.2. So the current is 3. This is the current. The distance here is R. So plug it in, and indeed you find 1.2 times 10 to the negative 5 Tesla. So at a distance R, so that's a distance R, that's going to be the magnetic field. Agree? Again, the current is going up, the magnetic field is circling around. Okay, that's your first right hand rule. Current is up, magnetic field is circling around. So I know that the magnetic field is going to be in this direction, but it's going to be all around. Okay, it's tangent. It's going to be tangent to that circle here. Everywhere. But then here you have a positive charge. So that will be the third right-hand rule. The positive charge is moving in this direction. You have the magnetic field in this direction. So you're going to have a force here, the magnetic force, perpendicular to the velocity and to B. That force will deflect. It will deflect the charge. So it will make it will deflect it this way, right? It wants to go in a straight line at a constant speed. No, no, you can't. It's going to be deflected. Okay. So what's the equation for the force? QVB, huh? the force is, what's the equation? You have QVB, right? Did you say QVB? Okay, let's see your equation here. No, that's calculus. The force here is QVB. So the magnetic force is Q times V times B, and here you have the sine, the angle between B and V. But this is 90 degrees, so that's going to be 1. So you don't have to worry about that. Are you with me? Right? So the force will be the charge, which is 6.5 times 10 to the negative 6 times V, the velocity, which is 280, times the magnetic field, which is 1.2 times 10 to the negative 5 times 1. Yeah. Yeah. Very good. 2.18 times 10 to the negative 8. 8 or 7? I found maybe it's 8.
I go to the 8.
To the 8?
2.1.
Okay.
Times 10.
So it's 8. 2.18 times 10 to the negative 8. Any question? Yes? So make sure to keep track. You have to keep track. So this is this equation there. I have a very nice slide that explain again. Okay, you see this slide here? So the magnetic force is Q VB times the sine of the angle between V and B. Okay, but most of the, like for you, for this class, this angle here will be either 0 or 90 degrees, so you don't have to worry about that. See, this is the equation here, QVB. Any question? Oh, I'm lost. Okay. You see, that's the equation of the force. Q, V, B. That's the angle between V and B. And B is from the stretch wire. So the angle here is between V and B. It's 90 degrees, so it's going to be 1. Okay? Make sure you do your assignment as you go along. Okay. So because current carrying wire, okay, they produce magnetic field. When you're gonna have two wires, right, they're gonna interact with each other. You see, because this wire is gonna make a magnetic field here. So you can take your right hand again. This wire, this one, I'm talking about that one, is going towards you. So at that location here, it's going to make that magnetic field here. So therefore, you're going to have a force here. So I'm going to summarize. If two current is going in the same direction, they're going to attract each other, okay, because the two magnetic field will interact with each other. And if they go opposite to each other, they're going to repel each other. Okay, so typical conceptual question again. If the current goes in the same direction, because the magnetic field are interacting with each other, they're going to attract. If they go opposite direction, the wires will repel. Is that clear? Opposite direction, they repel. Same direction, they attract. Okay? And that will be the equation for that. So I'm going to see if I have a video for that. No, that's the jumping wire. I have a video, except I have so many videos that I don't know what it is. Ah, here. Look, 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 look. So you have a power supply. Current is going to flow through those wires. In one situation, the current will go in the same direction because they are in parallel with each other. And in the other situation, the current will go in opposite direction because they are in series. So that means they go in the same direction, they attract. They go opposite direction, they repel. Isn't that cool? Right? It's amazing. So another equation yet. So that will be the equation for two currents. Oh yeah, I know another equation. And then I promise it's going to be much easier. It's just equation that you should keep track of, right? So the force between two current carrying wire, the force per length, so that will be the length of the wires. It's going to be I1, I2, and then it's going to be 2 times 10 to negative 7. And that here you have the distance between the wire. Right? So if you have a current I1 and the current I2, are they attracting each other or repelling each other? They go,
Same way.
so they attract. They go in the same way, they love each other. Okay? And then if I1 goes this way, I2 goes that way, they hate each other, they don't have the same political view, so they gonna repel each other, they hate each other. I hate you, I hate you. And that will be the equation. L here is, imagine you can connect that to a power supply, plus, minus, and then here you have plus, minus here. L is just the length here of the wire. And that will be the force between them. Okay? So that's why if you go by, I don't know if you know Sunny Eyes, there is a bridge and you have big transformers. And if you pass by, you hear, why is that? Because all those wires, because it's AC, they keep attracting, repelling, attracting, repelling. So you hear a hum. They oscillate back and forth. So two electric wires interact with each other because they both produce magnetic fields and the magnetic field interact with each other. Okay, so I think there is one question like that for test number 3. I'm going to give you some time to think about it. So you have a current I1 and you have a loop of current. It's like a thought experiment. What do you think? Do you think they're gonna attract? Is the loop gonna be attracted here or repelled? They go into a circle. So you have a current going this way and you have a current going that way.
Like now, my anything and the wire and so.
It's just one wire there. Don't give too much thought. It's just, let's say you have a current going this way and here you have a current going that way. So you have a loop here. You have a loop of current. It's just a loop. Okay, like a coil. Like something like this. You have a loop of current and at some point here you have a power supply. Okay, so it's the loop. So you are looking at the loop from above. So this and that, do they attract or do they repel? Huh? I don't hear you.
Which one is
They attract. This one and this one attract. Okay, but remember the force is inversely proportional to the distance. Okay, so I2 and I1, so this one and that one, that segment and that segment here, do they attract or they repel? This one and that one, do they have the same direction or opposite direction? They have the same direction? This one, the bottom one, at the bottom. Opposite or same direction? Opposite. So do they attract or repel? Repel. You know, you don't have the same opinion, you hate each other, they have the same opinion, you love each other. Okay, so same opinion, you love each other, opposite opinion, you hate each other. Okay, so it's going to be attracted here and repel here. Which one wins? Attraction or repulsion? Which one is the closest? Huh? Attraction wins because it's the closest, right? The force is inversely proportional to the distance. Okay, remember from physics 1, when we find the net force. So here you have a distance r1, and let's say here you have a distance r2. They love each other. They have the same opinions, political view, everything's the same. So okay, I love you too. Okay, so that will be the force F sub 1. And then this one, they hate each other. I'm looking at the force acting on the loop. So they repel. I hate each other. Go away. I don't like you. You smell bad. Okay. Repel. Okay, so the net force is going to be up. Let's say up is plus, down is minus. So it's going to be F sub 1 minus F sub 2. So the net force is going to be up. So they will attract. Does that make sense? Because the magnitude of the force is, okay, the length, the segment here. So that will be your length. But I1, I2 over the distance. So as you increase the distance, the force will get weaker. So this is the winner. And remember from physics 1, what's the system you are looking at? You are looking at this. Okay, so this is the system here. So the net force will be up. It's your black box. You survived? Any question? No equation. Sorry. Let's look at the summary. Let's see if we have everything. Let's look at the summary. You're gonna hate me today. There are so many equations. That will be the magnetic field of a wire. That's the equation for that. That will be a magnetic field at the center of the loop. That's what we are getting to. This is on the test number 3, so we need to get that. Get to that. Are you okay? We good? Okay, so now we go back to the loop. Remember the loop? If you have a loop of current, right, with your right hand, that's going to be the magnetic field there. Right? Do you agree with me? Okay, so you're going to have an equation for the magnetic field at the center of the loop, and that's going to be your equation. Okay, it's just an equation. That will be 3 equations for today. So, right? Let's get through that, and then we will review next time. But that will be the equation for the magnetic field here at the center of the loop B. Okay, so we have the magnetic field of a wire. We did that. Okay, of the wire, it's going to be 2 times 10 to the negative 7 I over the distance from the wire. And here we have the loop. So the magnetic field at the center of the loop, the equation looks the same, but you're going to add a pi here. Okay, so you have 2 equations here. Or you can use this one. It's just a shortcut. So let me show you the big idea. Okay, so this is the magnetic field of a straight wire. That will be the magnetic field at the center of the loop. Except, again, I forgot I here and I forgot I there. That equation here is the equations for the force between 2 straight wires. Agree? You survived? Okay, just equation. Oh, look at how nice I am. I summarize everything. So if you have a straight wire, again, you take your right hand. The thumb is the current. The magnetic field is going to circle around at a given distance from the wire. That's going to be the equation for the magnetic field. If you have a loop of current, okay, then you take your right hand, your fingers will be the loop, the thumb will be the north, right? And at the center here, you can find the magnetic field. Okay? So this one, if I do it, it's not going to help you. So I'm going to ask you to do it for Wednesday, Thursday, to do it for Thursday, because it's going to be for test number 3. So you need to know how to deal with that. Okay? Because you're going to have 2 equations. Okay, you're going to have here. So do that for Thursday. I trust you. Okay, you're going to do it. So you have the magnetic field at point C produced by the current I1. That's a loop or it's a wire? Very good, it's a wire. So I'm going to use the simple equation, 2 times 10 to the 7, and then have the current I1, and that will be at a distance R here. Okay, so circle around. And then I have the magnetic field produced by the loop. And the magnetic field produced by the loop, okay, it's the same equation, but there is a pi somewhere. A loop, you need to add a pi. And here is the radius of the loop. Okay? So you have two equations. If you have a wire at a distance r, you're going to have a magnetic field, which is 2 times 10 to the negative 7 times the current divided by r. If you have a loop of current and you want to find the magnetic field here at the center, then you use the equation, the same equation for a loop, except you use a pi. So how can you remember? So that will be the radius. You remember because when you think of a circle, you remember 2 pi r squared. So remember that for a loop, you're going to add the pi here, and that distance here is just the radius of the loop. Okay, so that's going to be the equation for the magnetic field at the center of the loop. That will be the equation for a magnetic field at the distance r from the wire. Okay? Yes. Yes. Yes, exactly. So you have a pi. Okay, and how do you remember? You know that a circle is 2 pi r square. Exactly. Okay, so you can add those equations to your equation sheet so it will be easier for you for the assignments. Okay, so you do that for